Hi, welcome to lecture number 59 of fuzzy sets, logic and systems and applications. In this lecture today, I will discuss Tsukamoto fuzzy model. Tsukamoto fuzzy model is a very special kind of model where we have the consequent part of the fuzzy rule monotonically increasing or decreasing membership function. So it looks like that this fuzzy rule has a crisp function, but actually the consequent part of the fuzzy rule of this fuzzy model, that means Tsukamoto fuzzy model, is always represented by a monotonically increasing or decreasing membership function, and the highest value of this membership function can go up to 1, not beyond that. So in nutshell, I can say that Tsukamoto fuzzy model involves the fuzzy rule, a set of fuzzy rules of the form where its premise part is fuzzy and the consequent part is also fuzzy. But the consequent part here is not exactly a fuzzy set that we have seen in the case of Mamdani model or the Larson model, but it is different here. This fuzzy set is different here. The consequent part of the fuzzy part of the fuzzy set is different in the sense that this fuzzy set of the consequent part is represented by or characterized by a membership function which is monotonically increasing or decreasing. So if this is the case, then the fuzzy set of this type, which is characterized by the monotonically increasing or decreasing membership function, will always be of this kind, like either it is left open or right open fuzzy set. So this is right open, and this is left open. So this kind of thing with the consequent part happens, and here, as I mentioned, that the consequent part of the fuzzy rule is fuzzy, like we have in the case of Mamdani fuzzy model and the Larson fuzzy model. The Tsukamoto fuzzy model also has the fuzzy rule of the kind of the type where the premise part is fuzzy and the consequent part is also fuzzy. So this has to be noted very clearly. Now the inferred output of each rule, please understand carefully here that the inferred output of each rule, each fuzzy rule, is a crisp value, and this is found corresponding to the firing strength, that means the weight of that particular rule. So the overall output is taken as the weighted average of the output of each rule. So Tsukamoto fuzzy model basically avoids the time consuming process of defuzzification, because here the final output is the weighted average of output of each rule. So that is where this makes the difference. So let us understand the Tsukamoto fuzzy model. So here we have a rule as we have taken in case of Mamdani fuzzy model and the Larson fuzzy model. So the same rule is being taken. So this doesn't need any explanation here. And this rule has the premise part where we have two antecedents connected by and or connective, and then part we have the which is known as the consequent part, and this is Z is Ci, and I here signifies the ith fuzzy rule. So in any model, any fuzzy model, we can have any number of rules. Say here we have n number of rules, small n number of rules. So that is why I has been used here, and this is our ith rule. So I can represent this by Ri. So ith rule can be if small x is ai and or y is bi, then z is ci, where I can go from 1 to 3 up to small n, and fuzzy sets ai, bi and ci are expressed as you can see here. Similarly, B fuzzy set and then the C fuzzy set. The firing strength of ith fuzzy rule is defined by here the Wi, this is for ith rule, so that's why Wi has been written, and then here the mu ai of x, and then we have a mean sign, the open triangle sign, and then here we have mu bi y. So, and this is mu bi of y. So what are these values? Basically, these are the values corresponding to the input that we feed, that we apply to the model, and corresponding membership values will give us the weights, and then these weights basically after taking either min or product will give us the firing strength of the rule or weight of the rule. So when we have this firing strength of the rule available, then the overall input can be found by taking the weighted average of the output of each rule. You can see here like this. So Z star has been used. So please understand here that we do not use any union of the outputs of the rules. Means we are not taking the union of the outputs of the rules that are applicable for the particular input. So let us now move ahead and have the cases of single rule with single antecedent, and then single rule with multiple antecedents, then multiple rules with multiple antecedents. And these cases we'll be discussing with fuzzy inputs as well as the crisp inputs. Here, as I mentioned, that the Tsukamoto fuzzy model doesn't follow strictly the compositional rule of inference. What is that compositional rule of inference? This is max min or max product. So since here we are not taking the union, so max is not applicable. Here the output is the weighted average of the outputs that are coming out from each rule which are applicable. So let us now discuss all these cases one by one for the fuzzy inputs and the crisp inputs. So let us discuss first the single rule with single antecedent here. So as we already know that if we have a model, fuzzy model, let's say called a Tsukamoto model. So Tsukamoto model is characterized by only one rule, that is single rule, and which is of this type where we have single antecedents, like if x is A, then y is B. So if this is the rule that is there for the model and this rule is known, now if a new input comes to the comes to the model as the input, here x is A dash. A dash is nothing but, what is A dash? A dash is fuzzy set, some fuzzy value. Fuzzy set or fuzzy value, fuzzy set is used for describing or quantifying the fuzzy value. So I can write here the fuzzy value. So if this is the case, then our output corresponding to the x input, that is fuzzy here, will be this. So we'll discuss this here. So if we have a single rule with single antecedent, which is here, so x is already there, then corresponding to this x is A, we have the output which is B, and this is the B fuzzy set. And please note that here the premise part has a fuzzy set which is a bell-shaped fuzzy set, whereas the consequent part, you see, the fuzzy set that we have here is the left open fuzzy set, and the highest value of this fuzzy set is going up to only 1, and this is monotonically decreasing fuzzy set. So let us, I can write here the monotonically decreasing fuzzy set or monotonically decreasing function, the fuzzy set function. So, and this is actually the fuzzy set. So here this is the rule that is given to us for the Tsukamoto fuzzy model. So here a new input, this is a new input which is coming, new input, I can write here new fuzzy input that is coming here. And if this input is coming to the model as input, to the Tsukamoto model as input, so what we do, we try to superimpose this fuzzy value, this fuzzy set, on the fuzzy set A, which was already given, which is already given in the rule. So A is already there, so A we already have. So we try to superimpose A dash with A, and then we find the intersection point, if any. So here we have the intersection point which is called weight, and I can represent this by W. Since this is the for the first rule, I mean here you have only one rule, so I'm not writing W1 or W2 like that, but I can simply write W. So W represents the point of intersection, and since we have only one antecedent here, so we are not going to use any compositional rule here like min or product. So this W is our strength of this rule. So W is here basically 0.58. This W is equal to 0.58. Now when we have this W available, this is also known as the firing strength of the rule. So when we have this, now corresponding to this point here, we try to find the Y. We see here that this is nothing but the mu x. That means the membership function, membership value corresponding to the x. And here this is mu y. So corresponding to 0.58, we try to find the y1, which is here. So y1 is, you can see the y1 here, y1 is 4.88. So this 4.88 is the value, the crisp value which we are getting corresponding to the fuzzy input that we are feeding to the model, to the Tsukamoto model, which is which has the single rule, which is characterized by the single rule with single antecedent. And the input is fuzzy here, that is A dash. So the interesting point here is that we always get a crisp output of the rule. Means even if we provide the fuzzy input, we are getting the crisp output, which is y1 here. So y1 is, for this case, 4.88. Now since we have only one rule, so the weighted average is going to be the same. Here it is W1, which need not be there. So I can write here W1, okay. And this W corresponding to this this rule, the output is 0.58. We have Y star is equal to W1 into y1 over 1, and so we are getting 4.88. So here the weighted average is going to remain the same. Now what if we have the crisp input? So if we have crisp input, x is equal to x1, the output here is going to be y1, and let's see how do we find the corresponding output here for the crisp input. So here we have the rule, and corresponding to this rule, we have the fuzzy set A that is already given. Now we have the input, some input, let's say x1 is equal to 6.8. So we have taken x1 is equal to 6.8, which is lying within the region of universe of discourse, and also it is lying within the region of the fuzzy set A. If it is not lying within the region of fuzzy set A, this rule will not be applicable. So this input has to intersect the fuzzy set before the rule can be applicable. So here we are taking x1 is equal to 6.8, and corresponding to this input we are getting the intersection point, which is, let's say, W1 here, and this W1 is equal to 0.34, and this 0.34 we have got, this is called the rule strength, fuzzy rule strength, or strength of the fuzzy rule. This is also called the weight of the rule. So Corresponding to this, now coming to the consequent part fuzzy set, which is here, and corresponding to this, we are getting the corresponding to this mu y, this becomes mu y is equal to 0.34. So corresponding to this, we are getting our y1 here as 5.21. And again, since we have only one rule, so we have only single rule, so the weighted average is going to remain the same. So this way, even if we have the fuzzy input or the crisp input, for this case, for this model, the Tsukamoto model, where we have only one rule with single antecedent, we are going to get the crisp output, and the output calculation is very simple. We are not going to here apply here the compositional rule also. It's not actually applicable, because the min, if we are, let's say, apply the max min composition, so min will not be applicable, or product even will not be applicable, because we have only one antecedent. Similarly, the max is not applicable, because here first of all we have only one rule, but even if we have more number of rules, then also the output is the weighted average of the outputs of the rules. Now, let us come to the other case, the second case. Second case here is that we have a Tsukamoto model, and let's say it is characterized by the single rule but with multiple antecedents. So we have single rule, let's say, and then this rule has multiple antecedents. So let's now look at this rule and see how does it look like. So we have here this rule where we have only one rule. The model is characterized by, model is represented by only one rule, where we have here in this case we have two antecedents. So we see that we have first antecedent as x is a, and the second antecedent in this case is y is b, and both of these antecedents are connected by the connective and. So instead of and, it could be any other connective like or, but, etc. So when we say single rule with multiple antecedents, so multiple antecedent can be any number. Here we have only two, we can have any number like 3, 4, 5, 2, 3, 4, 5 and so on. So here for simplicity, we have taken only two antecedents, and these are joined by, connected by the connective and. So this is connective, as we already discussed. Alright, so next is to find the output, final output corresponding to some input. So we'll go ahead and first apply the fuzzy input. So here we have the single rule, rule is here, but here we have two inputs, the input 1, which is x is equal to, which is input x is equal to a dash, this means the fuzzy input is provided, and then the another input simultaneously fed is y is equal to b dash. So these two inputs are together supplied to the model. Now let's see how will this rule help us in finding the corresponding output. So like we have done in the past, what we do here, we superimpose the inputs, the fuzzy inputs on A and B respectively. A and B are already there in the fuzzy set, in the fuzzy rule. So here we see that when we superimpose, we find the intersection. Here when we superimpose, we get W1, and then we get here another intersection here, which is W1. So this is, let's say, W1, and this is, let's say, W2. Now, since we have here two antecedents, now if we use min composition from max min, so the W1 becomes min of the W11 and then here W12. So the firing strength of the rule, firing strength of rule becomes W1 is equal to 0.36, and corresponding to this 0.36, the Z1, which is the output fuzzy set, we get Z1 is equal to 5.19 here, and it is very clear from this picture. Here. So our Z1 is Z1 corresponding to X is equal to A dash and Y is equal to B dash here. And since we have only one rule, so the weighted average becomes the same. So this is weighted average. And since we have only one rule, as I said, the 5.19 will become the final output. Now, what if we supply crisp input to the Tsukamoto model characterized by single rule with multiple antecedents? So let us see that here we are supplying x is equal to x1, some crisp value, and y is equal to y1. Here x1, y1 are the crisp values that are being supplied. So let us take x1 is equal to 6.5, y1 is equal to 8.5, and when we apply this, when we use this x1 value and y1 value, we see that the rule that was given and that is characterizing the Tsukamoto fuzzy model, the rule is here. So this is actually known. So this rule is known. So when the rule is known, we can say the model is known. So all the parameters of this rule is known. Means A is known, B is known, C is known. So here, corresponding to this x1, we have the membership value is 0.81, which is called the weight here. So W1, let's say here W11, this is the first rule. So first rule is W1, and then for the first antecedent, so W11, and then here corresponding to Y1, similarly we get, let's say, W12, and if we take the min composition here, so we take the min criteria, when we take the min criteria, so firing strength of the rule comes out to be, this is firing strength of the rule, which is coming out to be W1, and W1 here is 0.36, and corresponding to this 0.36, you see here, this is 0.36, and corresponding to this, the through the output fuzzy set, which is monotonically decreasing fuzzy set, we are getting Z1 here 5.19. So now, since we have only one rule again here in this case, because this is single rule with multiple antecedent model, Tsukamoto model, so the final output is a weighted average, and weighted average is going to be the same. So 5.19 is the final output, corresponding to x1 is equal to 6.5, y1 is equal to 8.5. Now let us go to the third case where our Tsukamoto model is characterized by the multiple rules with multiple antecedents. So we have here two rules. For simplicity, we have taken only two rules, but it can be any number of rules, say up to n. And similarly, we can have antecedents here, any number of antecedents. Here we have, for simplicity, only two antecedents. So two rules and two antecedents for simplicity we have taken. Now, if we supply the inputs to this model, to this Tsukamoto model, which is characterized by the multiple rules with multiple antecedents, let's see how we get the output, final output computed. So here we have the rule number 1, I write here as rule 1. So rule 1 basically has A1, B1, C1 fuzzy sets which are known to us. All the parameters of this rule are known. Similarly, we have rule 2 here, and here also A2, B2, C2 are known. So when we feed the input, X is A dash. A dash is a fuzzy value. Similarly, Y is, let's say, B dash, which is again a fuzzy value. So when these two fuzzy values are supplied to this model, let's see the how the output, final output, we can compute. So X is equal to A dash, Y is equal to B dash when it goes to the, when it applies to the first rule. So as we have already done, we superimpose this fuzzy value, these two fuzzy values, to the fuzzy sets that are already present in the antecedents A1 and B1 respectively. So here this is the antecedent for X, this is the antecedent for Y. So we superimpose A dash with A1 and we superimpose B dash with B1. B1 is known, A dash is known, A1 is known, B dash is known, A1 is known. All are, the fuzzy values are known. So now we look for the intersection points. So here, since this is the first rule, I am writing W1, and then first antecedent we write 1 here. So W11 here is 0.86. Similarly, for this antecedent, the intersection point is W12 is equal to 0.36. This is 0.36. Alright, so now if we apply the min of these two, so the min is going to be here, the rule strength is going to be 0.36, and corresponding Z1 here, we see that the corresponding Z1 here is 5.19 for the first row. Similarly, when we apply the same input to the rule 2, these points are coming out to be, the weights are coming out to be here W21, and then this is W22. So W21 is 0.58, and W22 is 0.35, and if we take min of this, we are getting here as W2 is equal to 0.35. So this is rule strength of 1, and this is the rule strength of 2. Or I can say here the firing strength. It is more appropriate to write firing strength of rule 1. So this can be written as firing strength of rule 2. And here corresponding to W2, you can see here corresponding to W2, we are getting Z2, that means the corresponding output, 4.79. So please note that here we are getting two outputs, Z1 and Z2. So we are getting Z1 and Z2 output. Z1 is corresponding to the first rule, Z2 is corresponding to the second rule, and both these outputs are, the rule outputs are corresponding to the input, fuzzy input A dash, x is equal to A dash, y is equal to B dash. Now the next step is to, since we have two outputs from the rules, two rules, so we go for the weighted average of it. So weights we already know here. This is our W1, this is our W2, and here this is our Z1, 5.19 is Z1, this, and 4.79 is Z2. So when we take weighted average, we already know the formula of the weighted average. I can once again write it here. So Z star is nothing but W1 Z1 plus W2 Z2 over W1 plus W2. So this way we compute the final output as 4.9928 corresponding to the fuzzy input x is equal to A dash and y is equal to B dash. And please note that this model, this is the outcome of the model, Tsukamoto model, with multiple rules with multiple antecedents. Now, what happens when we supply the crisp inputs? So here everything remains the same. The input becomes crisp input. X is equal to x1 and y is equal to y1. So now let's go ahead and see. Here we have the rule 1. Here we have the rule 1. And in this rule 1, we have the crisp input. So when we apply this input, crisp input, x1 is equal to 7 and y1 is equal to 6.5. So corresponding to this x1 is equal to 7 and y is equal to 6.5, we get 2 points of intersection here. So for the first antecedent where we have A1, for A1 we are getting this value, this x1 is equal to 7 is giving us the intersection point at 0.28. So this I can write as W11. Similarly here, why W11? Because this is for the first incident and antecedent and first rule. Similarly here, this is first rule and first antecedent. So sorry, this is second antecedent. First rule, second antecedent. So W12 is 0.97. Now if we use min, so min of these two is going to give us W1, which is, as I mentioned, the firing strength here, firing strength of the rule 1. So corresponding to this W here, corresponding to this W1 rather, corresponding to this W1 here, we are getting the output Z1, and Z1 is here Z1 is 5.31. So the outcome of the rule 1 is Z1, which is 5.31. Similarly, now we go to rule 2. So here we have rule 2. Now the rule 2 here gives us the intersection points like this, the W1. Since this is the second rule, so we will write W21 and then here we'll write the W22, the second rule, second antecedent. So corresponding to the Y1 here, which is crisp 6.5, we are getting two values, two intersection points, and when we take min, we get the firing min of these two will give us W2, and W2 is nothing but the firing strength of the rule 2. Firing strength of rule 2. Now we have corresponding to W1 Z2 here, and Z2 is 4.4. So now these two inputs we already have, Z1 and Z2. Now let's go ahead and find the weighted average. So weighted average is giving us here Z star, which is the final output, and Z star is equal to 5.0067, and we already know that we have our W1 0.28 and W2 0.14 and 5.31 as Z1, 4.4 as Z2. So if we substitute all these values here, Z star is W1 Z1 plus W2 Z2 over W1 plus W2. So this is giving us Z star is equal to the final output corresponding to x1 is equal to 7, y1 is equal to 6.5, we are getting z star is equal to 5.0067. So this is how, corresponding to the crisp inputs with multiple rules and multiple antecedents, which is describing the Tsukamoto model, we are getting the output. Now let us take a very simple example here of Tsukamoto fuzzy model, where we have three rules. So this fuzzy rule is defined by, this fuzzy model is defined by three fuzzy rules. And this rule, as we see here, these three rules are of the type of multiple antecedents. So we see the premise part, we have two antecedents in all these three rules. So this is of the kind of model, fuzzy model, Tsukamoto fuzzy model, which is the multiple antecedents and multiple rules. And the membership functions here are already known, as since the model is known, so membership functions have been given here: mu a low, mu a medium, mu a high, mu b low, mu b medium, mu b high. So here we have this model has two generic variables as inputs, x and y are input generic variables. Z here is the output generic variable. Output generic variable. And please understand that the x, the complete x, is divided into three fuzzy regions: low, medium, high. So this means that these fuzzy regions have these fuzzy regions are characterized by three fuzzy sets, and the membership functions, corresponding membership functions here are mentioned. You can see here for the input, and similarly for the input y. So for input x, here input x, and then here we have input y, generic variable. So we see that in both the input generic variables, we have three fuzzy regions, and in the output here z, we have only two fuzzy regions, and both the fuzzy regions are represented by fuzzy sets. Here the sigmoid fuzzy sets, low and high. The input x region has three regions represented by three fuzzy sets. All the fuzzy sets are trapezoidal type. Similarly here, input y also, all the fuzzy sets of the three fuzzy regions are trapezoidal type. So now when we give the input, the crisp input here, the crisp input, so for this crisp input, what will be the corresponding output, and that too in crisp form. So let's now see as to how we can find it. And the universe of discourses of the inputs and outputs are mentioned here. So the fuzzy regions, the membership functions that are given, if we plot the fuzzy sets will look like this: low, medium, high. Similarly here also this will look like this. So all of these are given, these are known, so we don't have to worry for the parameters of these fuzzy sets. These are already given here. You can see these are the membership functions which are characterizing the corresponding fuzzy sets. So let us apply the input. And what is the input here is x is equal to 65, y is equal to 55. So these two, this input has two parameters: x is equal to 65, y is equal to 55. Both these values are now applied, and since we have the three fuzzy regions, so the first step here is to find where it is intersecting, where this x 65 is intersecting. So this line, when we see, is intersecting at here 2.25 and then 0.75, you can see. So this is the first step. First step is to find the corresponding to the input, that is here 65. So see, corresponding to 65, what are the fuzzy regions which are applicable? What are the fuzzy sets that are applicable? So please understand that this x is equal to 65 is intersecting medium and high only, not low in this case. So low is not relevant. Only medium and high are relevant for x is equal to 65. This is the first step that we check while we are computing the output. So step number 1 I can write here. Next is, similarly we check for the other antecedent, like y is equal to 55. So y is equal to 55, we see that this corresponding to y is equal to 55, we are getting high and medium. Medium is not intersected because it is when we see where y is equal to 55 is cutting at medium, medium is at 0. So we see that medium is not relevant. Only high is relevant. High fuzzy set for high is relevant. So y is equal to 55, only one fuzzy set is applicable. Now, or in other words, we can say that low and medium are not at all applicable. So we have for x is equal to 65 two intersection points, whereas for y we have only one intersection points, y is equal to 55. Now we multiply these two, means two intersection points and then the one intersection point for the other intersection. So 2 into 1 means we have 2 into 1 is 2 here. So only two combinations are happening here. What is that combination? The combination is when my x is medium and high, or what is the other combination here? When my x is high and high. So we have two combinations. I can write here the medium, I can write x here and y here. I can write medium by m and I can write high by h. So first combination could be the medium high, and then other combination, the next one is high, because the x is 65 is cutting high fuzzy set also. So high and high. So two combinations we are getting. Now corresponding to these two combinations, what will be my output, that is z. So this we can find by the rules that are given. So let's now check here. The given rules are here. So first rule here is, the rule number 1 here is, when my input is A, when my input is low, input A is low, or I can say input 1 is low, and then my input 2 is medium, then the output, or I can write here x, y. So input x is input y and output z here. So my input x is low, the output y is medium, then the output z is going to be low. This is z. So this rule 1 is not applicable, because we see that we have first combination medium and high, the second combination is high and high. Here we see that low and medium is not applicable. So we are not seeing any combination which is low and medium, so this rule will not apply. Now next we look for medium and high, which is here. So rule 2 is applicable, where we have medium, high, x is equal to medium, y is equal to high. I mean, when x falls in the medium, y falls in high, then the output also falls in high. We can see here this one. So this way, from this rule, we can very easily find the output is going to be, the z is going to fall in high region. So I can write here high. Similarly, what happens when x falls in H and y falls in H? So when x falls in H here and then y falls in H, output also falls in H. So this rule is already there. So rule number 3 also applies. And with this combination, we can write here high. So it means both the outputs are from high fuzzy region in the output. And these are the computations that we do for getting the corresponding membership values, which are nothing but the intersection points here. For x is equal to 65 here, for low, for medium, for high, and similarly for the other antecedent, the second antecedent here, y is equal to 55, y is equal to 55 here. So for low, medium, and high. So this way we get the points of intersection. Alright, so now when we know these rules which are applicable, these two rules are applicable here for the input that we are supplying. Now let us compute the corresponding outputs. Now this is very simple. We have already done this. So rule number 2, we have medium, high and high. So when we have the input 65, we see the points of intersection. See here. So this I can write W1, 1, and similarly corresponding to Y input, we get the W1, 1, W1, 2. So our first step was, let me just recap. The first step was to get the points of intersection in the fuzzy regions. Means we need to first find all the combinations corresponding to the inputs that we are supplying. So we need to know what are the fuzzy sets that we are getting intersected, that are applicable, and that's how we make the combinations, and these combinations we check with the given rules. So then from these rules we find that what are the corresponding outputs. And so here in the given rules we find, we we check what are the applicable rules. So these are the applicable rules here. So the given rules are normally more than the applicable rules. All right. So this way, when we have come to know the what are the rules that are going to be applicable, so this I can write as the step number 2. Next is same as what we have done in this lecture, like for particular inputs, how do we get the output for the case multiple antecedents and multiple rules of Tsukamoto fuzzy model. So now when we apply x is equal to 65, y is equal to 55. So since rule 1 is not applicable, so we have not written here, only rule 2 is written here. So we are applying this in these two inputs in rule 2, and then we find W1 1, W1 2, and corresponding to this we have here the firing strength of the rule 1, which is nothing but the W1 is equal to 0.75 if we take min. Similarly, here this is W21, this intersection is W22, and if we take min of these two, we are getting here W2, which is the firing strength of the rule 2. Now, corresponding to W1 here, the Z1 that is coming out to be 57.197. Corresponding to W2, the firing strength of the rule 2, we are getting Z2 is equal to 52.803. Now, when we have gotten these two values, these two outputs which are coming from rule number 2, rule number 3 respectively, now we take the weighted average of this. So weighted average will be Z star, let's say we are interested in final output. So final output will be W1 into Z1 plus W2 Z2 over W1 plus W2. Let us now quickly, here we are here. So let us now quickly substitute these values, and our Z star becomes here finally Z star is 56.0985. So this is the output corresponding to the input that we have supplied. Here one thing that needs to be noted here is that even if we use rule number 1, our inputs that are here, x is equal to 65, y is equal to 55, it is not cutting, it is not giving any intersection point. So that is why we have, through that step 2, through step 1, step 2, we have already filtered that. So we are not going to get any point of intersection even when we use rule number 1. So in this process, right from the beginning, we have found out what are the rules that are applicable, where we are getting the points of intersection. So this way, using rule number 2, rule number 3, we are getting our Z star is equal to, the final output is equal to 56.0985, corresponding to the crisp inputs x is equal to here 65 and 55. So this way we have seen that as to how we can use Tsukamoto fuzzy model to find out the output corresponding to the crisp input or fuzzy input. So with this, I would like to stop here, and in the next lecture I will discuss the TSK fuzzy model. TSK fuzzy model is nothing but the Takaki, Sujeno and Kang fuzzy model. Thank you.